Okay, so moving on, we're going to discuss the mean value theorem. This is section 3.2 in our book. And first we have Rolle's theorem. Let f be a function that satisfies the following three hypotheses. We have one being f is continuous on the closed interval ab, f is differentiable on the open interval ab, and f of a is equal to f of b. Then there is a number c in AB such that f prime of c is equal to 0. And so what are we looking at? Well, we'll kind of prove this, and I'll kind of show you some pictures of what this thing's talking about. So let's look at the first one. If f is a constant, then we have a flat line. Sorry, it's as close to flat as it's going to be. F of A, this is A, this is B, and there's some C somewhere in here. We don't know what it is. It could be anything in there, but this is really straightforward. If we assume that f of x is a constant, then f prime of x is equal to 0. That's a given, right? Because the derivative of a constant is 0. And C can be any value inside AB. Okay, so it can be any value in here. It will work. Sorry, it wasn't letting me draw it. And so we've already proved that. So that's that. Now let's look at the next part. Well, let's consider if f of x is greater than a for some value in there. So what this says is for some x existing in interval ab, that I don't think such that isn't needed. So it says there exists an x inside of the open interval ab, such that f of x is greater than. Oh, I guess such that does work there. F of x is greater than f of a. So by the extreme value theorem, this is what we talked about the last section. Extreme value theorem. Since we know number one was f is continuous. On closed interval. I'm not going to write closed though, because we know it's closed because I'm going to draw the brackets. AB. We know f has a maximum value in AB. We know that because that was the theorem we did in the last section, and it basically told us that if f is continuous on a closed interval AB, then we know it has some maximum value in that interval. Okay, and now since f of A is equal to f of B, the maximum must occur. That is not how you spell occur. At C existing in the closed interval AB, or I'm sorry, the open interval AB. And so, right, if A and B are equal, and we know that some value is higher than A at the very least A, well then it's also higher than B. And so there's a maximum somewhere in there that is inside the open interval that doesn't include those endpoints, that is considered the maximum for this interval. And so then f has a local maximum at C, and by, that's ugly, by Fermat's theorem. That was the last section as well. F prime of C is equal to 0. Okay, which is what we wanted to show. Because remember, the final premise of this is that then there exists a number C in AB such that F prime of C is equal to 0. Now, for the last part, there exists an X in the open interval AB such that F of X is less than F of A. This is going to be pretty much the same exact thing as this theorem here in the middle. You'd kind of just read exactly what you wrote. So by the extreme value theorem, I'm going to abbreviate it, EVT. We know F has a minimum value in the closed interval AB, and then since F of A is equal to F of B, then this implies there is a C existing in the open interval AB such that C is a local minimum, and by Fermat's theorem, F prime of C is equal to 0. And therefore we've proved all three cases, and now we know that Rolle's theorem actually holds by those two other theorems and being clever and doing cases. So another way to prove things, obviously basically the same proof for parts 2 and 3, but once you get 2 down, 3 comes with it. And so I hope this helps you guys understand why this theorem works, and we'll get into some examples here in a moment. Thank you guys.